all right, this is where you will see it. A good start to compression. Practically, compression used to be a very political topic. It's not just technology. Most of the well-known compression algorithms, if you can think of one new one, you will patent it. It's a cash cow. Once you got the idea, you patent it, you can just quit your degree and retire. Money is just falling from the sky. You don't need to do anything. And most of the compression algorithm, as you learn, like for example, BWT, as I said, it's very simple. 2 steps, 3 steps, that's it. It's very easy. You can't have a very too complicated compression because no one will use it. Too complicated, too costly. Most of them are very efficient and not too complicated. So it means like, wow, think about it. If as a computer scientist or IT expert, there's something in this world not complicated, simple, think about it, don't need to do it, protect it, that's it, sit back. Oh, you used my idea, $10. Oh, you used mine too, $10. After a while, everyone is just send you $10. That's it. Why bother to do anything? So that's why compression is one of the very hot area. You will see lots of patents. If you do a search, heaps of them. Now, it's same as many other areas like engineering, but within IT or computer science, compression and database storage are 2 of the hot topics within the patent world. Because once you patent, you protect that corner. Anyone walk into that corner, they need to pay the toll. And you just sit back and collect. So these are the areas. But if you're doing some other area, they're not as popular because people can avoid that corner. These are the areas that is harder to avoid. So give you one example. Stack is one of them. Stack versus Microsoft. Again, I guess for you guys, probably you never heard of that because I think Stack versus Microsoft probably before you guys were born. But for me, I was of course born, so I was there. So it's 1990 something, 1994. So Stack is a company, it's a startup company from a university called Caltech. In case you don't know where's Caltech, Caltech is in California. And if you watch the show Big Bang Theory, that's Caltech. So it's very good in those physics, astro study, and blah, 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 and so on. That's Caltech. And there's a bunch of people there, 5 students, I remember correctly, it's 5 students, and they formed a startup company, and they were doing hardware chips for data compression for hard drive. And they are helping a company doing that, and later they find out that, that piece of thing, idea, can also be in software. We don't need to make hardware chips for that. But they work for a company doing hardware. So they got this idea. Let's just quit. Don't do the chips. We do the software version. So they quit the company. And they decided to do the software version. And they found out it works quite well because at that time, hard drive is very small. In fact, very slow. And the CPU, although it's not powerful, but still much faster than a hard drive. So they decided to use the spare capacity of the CPU to do computation, which is called compression. And since you're waiting for the hard drive to do stuff anyway, I may just use those time to do compression or decompression. And then you can make the hard drive store more. And end up, it works. So the final product they do, it can make the hard drive store double amount of information without slowing down the hard drive because the hard drive is already very slow. So you get it for free. And the company they work for originally, they make a chipset to do exactly the same thing. Guess what? Can you still sell it? No, because those bunch of people got a software version. I think the company really, really regret that we shouldn't hire them. So they got the idea, they make the solution, and they kill you because you're selling hardware. So the product is called Stacker. And Mr. Bill Gates, of course, he knows everything. He also knows how to use everything. He also knows how to steal everything either. So, but it's not. Calling stealing is wrong. So he actually paid the money. He paid the money to Stacker, license the technique on their operating system before Windows. It's called Microsoft DOS, MS-DOS. But they also use it on Windows as well. So, and they license it, they use it. After they use it for a while, they decided, we can do our own one. So they make their own one. This is a typical Microsoft tactic. They do their own one. After they do their own one, they have their own one. Do you think they still pay you a licensing fee? Of course not. So they don't pay you because we have our own one. We call it a driver, just a plug-in driver to the operating system. We plug it in. It can also store twice the amount of information on the hard drive. Who need you? So they put it in. And these people, of course, a bunch of kids, they are not happy. So they decide to sue Bill Gates. They sue it and at the end when they sue, and then the court say that, okay, so Microsoft lost the case, pay you $5 per copy, that's it, go away. Then they are not happy. Of course, $5. I want almost $5. I want $10. So then they appeal, but they do the right thing. Because if you just keep asking for money, Bill Gates will say, okay, I don't pay you $5. I pay you $6, go away. And you're still not happy, okay, $7, that's it, still one off. But this case, they are very smart. They go one way. No, we are not interested in money anymore. We think it's not fair. So they put in court and ask the court, while doing hearing, block the sales of their copy first. Don't let them to sell until we have the verdict. So they block the sales of the Microsoft operating system until we have the result. And that will nail him down. Because they're like, oh, geez, well, you stop us selling, what am I going to do? You have to wait for the verdict. So then they stop selling operating system for a while. Then they settle the case outside the court and say, oh, guys, can you just cancel the case? We pay you. No, in fact, we are not going to pay you like $5, $10. We just buy your company instead. That's easier. So at the end, Microsoft pay, I can't remember, $10 per copies plus something like $43 million at that time to compensate your loss in the past few years, plus also buy a huge amount of shares of your company. That's everything. So they got everything from Microsoft. And that's the story. That's because of one compression algorithm that can do software compression to double the space of the hard drive. That's it. One patent. Now, having said that, after that, or during that time, everyone found that, geez, if I have one patent, I can really nail a company like Microsoft. So everyone go for a patent. Then, all of a sudden, you will have some crazy thing. It used to be only IBM, Microsoft, they put on those patents. Now you have I don't know, Mr. John Smith decided to put in a patent on compression. And Mary Jane also decided to put in a patent on compression. Everyone want to put in. My dog also want to put in patent on compression. So you have that. Then you have the patent office that totally screw up. You have this patent. A famous classic example, they usually, if you study law, like patent attorney in US, you study this classic case. It's called the compression case. Classic case, US patent 5533051, which have a claim. If you look at the claim, if you have a bit of common sense in technology, you will laugh. But apparently, it got approved by the patent office in US, and it's very smooth approval too. The patent claimed that they invent some magic compression algorithm. What it can do is this compression algorithm can direct bit encode method of the invention is an effective method for reducing an input string by 1 bit regardless of the bit patterns of the input string. You know what it means?
I'm guessing it means that they only store the 7 bits of the ASCII character that are actually part of the ASCII specification.
But it's saying that reducing an input string by 1 bit regardless of the bit patterns of the input string.
Would you just apply it indefinitely?
Yeah, you could keep doing this and finalize it.
Yes. We can also call it pipe to the def now, or remove the file, because eventually you're doing that, it becomes nothing. This is a true black hole, really, because you get nothing.
So it doesn't even work, basically?
They don't have an implementation. It's just a patent. It's during that period, I'm telling you, it's you got this idea, but you find that, you have a choice, like you have this compression idea. You have a choice of spending 2 weeks to write the program or spending 2 weeks to write the patent. They will say, write the patent first. Because it's not the program that get you the money, it's the patent that get you the money. You look at those cases. So if you have that's the atmosphere at that time. You come up with all this crazy thing. Some of them got rejected, but it's just like this one, it stand out because it got approved. And it's just ridiculous when it got approved. And then they use it like mock the patent office and say the patent office is so corrupted and this one. But it just showed to you that in a sense that like this compression and patents, it have lots of like stories between them. It's like most of the people work on compression, they will go for patents. That's the path to get rich. But how many of them are actually truly working? There's a big question mark. All right, so that is just to let you know the background, so you know patents and compression, they are quite related. So there are lots of good technique, good compression technique. Even today, you can't use it because it has been patented. We actually have the technology, but you can't use it because it's patent. And you're not willing to pay for that because it's probably cost you like, I don't know, $10 million just to use it for one software or something like that. You will never use it. But that's what happened. It actually blocked the usage of the technology. So now this is another example just to show you that like, you know, it's a simple fact, but you need to know that all the compression algorithms, they have some overhead costs. So if you compress some files, you may need to store extra information, maybe statistics about the file, maybe some extra overhead. So you keep compressing the file can actually get bigger, not smaller. Not because of the compression, fail or something, but you need to add the overhead to it. So if you keep gzip, for example, gzip need to put a table or header of the extra statistics information or housekeeping information there. So if you gzip a file, it compresses your file, and then you stick a header onto it to store the housekeeping information. So you keep gzip, you can't compress anymore. Then you just keep adding the extra header on top, then become larger and larger. So it's just telling you that like if you're using some external software to do compression, it's not necessary you get a smaller product at the end. It may be the final result of your compression is a larger file. Okay? Now, another sidetrack is like people use compression in a different way. There's a paper from 2004 from a research group, and there was a company, startup company, also after the idea of this paper, although it went bust very quickly, but you know, at least they tried to commercialize it. So the idea is that if two objects compress better together than you compress them separately, it means that they share some common patterns are similar. So it's amazing in the sense that how they thought outside the box, as in they use compression. So you can give them 2 text files, or 2 images, or 2 videos. They try to group them together and compress together, and compress them separately. If they group them together and compress, they find that they get better compression ratio. They will use this to detect that they share more similarity between these 2 things than the others that they don't compress better. So if you give me 2 text files, A and B, if I compress A and B separately, A.gzip and B.gzip, then if I group them together, called AB, AB.gzip, if AB.gzip is smaller than the A.gzip and B.gzip significantly, I know that there are lots of similarity in that file. That's their theory. And they use the compression for similarity detection instead of for compression. So it's a nice idea, as I said, but I don't know, for some reason that their business didn't work out at the end. Right. Those are just all the background information of data compression. So next is the real stuff. Anything before this slide is not examinable. Just in case. I wouldn't ask you how to spell Stack, the company suing Microsoft. Or I wouldn't ask you like who sued Microsoft in 1994 and who win. That wouldn't be the question, so you don't need to worry about that. So anything before this slide, you can forget about that. All right, from this slide onwards, it's the real stuff. All right, so compression refers to a process of coding that will effectively reduce the total number of bits needed to represent certain information. So you have some input data, you go through an encoder or a compressor or compression. And after you go through this encoder, hopefully the data becomes smaller. Then you can either store those data or transmit the data to the receiver side. So when the receiver either get it from your hard drive, which is your same program, or get it from the computer network, which is you send it to the receiver. When the receiver receives it, it needs to use a decoder or decompressor to decode the information and get back the data that is the same as the input data. So if it's lossless, what you input and output should be identical after going through this process. So you hopefully by having this, the media between them is the same information, but of the smaller form. So you can reduce the number of bits or make it smaller size and so on. There's a field in computer science called information theory. The field is invented by a person called Claude Shannon from MIT, I think back to 1940 something. It's a whole field. That field studies the efficient coding algorithm. It studies the complexity, compression, and the likelihood of error of this coding algorithm. Unless you're very interested in theory, luckily we are not going to study information theory in this subject. So in case you're scared of theory, you are fine. So we are studying more the applied aspect of the coding, not the theoretical aspect of it. But for those who are interested, as I said, you can look up those topics about information theory. They will cover the theoretical aspect of this coding algorithm. There are two main categories of compressions. Lossless, which is the input message is equal to the output message. The input is equal to the output. That's lossless. Whenever the input is not equal to the output, it's lossy. Lossy is not necessarily bad. It can enhance quality sometimes. Give me an example. Why lossy is good? You like to lose information sometimes. Why?
I just need to check the correctness. We don't need to recover this.
You may lose the correctness. Yes?
I think like denoising, maybe? Like if it's an image, it might actually...
Exactly. When you're taking photo of your girlfriend or boyfriend, you want it to be lossy because it looks nicer. Right? So in some situations, you don't want to know the truth. You want to be like a bit blur. That's good. So in some situations, we prefer lossy. But in some other situations, most of the real situations, serious one, you prefer lossless. So you just need to know that it's not like one kind is better than the other. Depends on your application. But there are two kinds. One is the input and output are the same. One is the input and output are not the same. Now measuring the compression. What's the compression ratio? So usually we measure the compression using the compression ratio is the uncompressed size over the compressed size. So it will be usually a number larger than 1. So on the other hand, you can measure by the space saving, which is 1 minus the compressed size over the uncompressed size. For example, let's say if I compress a 10 megabyte to 2 megabyte, that's 5 times compression ratio, or 5 to 1. But you can also measure as like space saving. You're saving 80%. It depends on how you say it. It's the same thing. It's a different way to say it. Okay? By the way, here, just in case, if you're reading some web articles, sometimes web articles, they talk about technology, they're not necessarily a scientist in the field, so they will using a more layman terms. They will be confused about what's compression ratio. Sometimes they will say compression ratio is 0.8, and we are fine with that. Sometimes they will say it's 5. So, but your gut feeling will be whoever tell you some number that's larger than 1, you know that they're using this formula. Whenever they tell you the number is smaller than 1, you know that they're using that one. Unless your compression totally screw up. It's like, that would be a different story. Like, maybe it's telling you, how worse is my compression algorithm? Yeah, when you're doing assignment, ask your friend, how is your compression ratio? When you say it's 5, then you can't assume it's that one. Maybe it's really bad. So, it depends. Terminology. Some boring stuff, but you need to know the terms. So, encoding or coding maps the source messages from alphabet S to the code word C. Source message, or we call it symbol, is a basic unit into which a string is partitioned. So the smallest unit in the input, we call it a symbol. Can be a single letter or a string of letters. Now, so the input can be one letter, can be multiple letters as one unit. The output is a sequence of bits, and that bit can be fixed length, like ASCII code is fixed length, or can be variable length. If the input is fixed length, output is fixed length, block to block, we have the block to block type of compression. You may have the fixed length input, variable length output that we are going to discuss soon. We will call this block variable type of encoding. It can be variable block type, means that you take multiple characters, map to the fixed size of bit sequence. That will be a variable block type of encoding. It can be variable to variable, which is you're taking multiple variable number of characters, map it becomes a variable number of bits, there will be variable. Each of them will teach you one technique on them, the classical technique. So the first one, block to block, is easy. It's ASCII code. We know that. Every letter, always one letter, becomes 8-bit or 7-bit, whatever you like. It's a fixed length. So that will be the ASCII code, is block to block. The next we're going to teach you is the block to variable, which will be Huffman coding. And then after that will be variable block. We will tell you the LZW, and then will be arithmetic coding. Compression can also be divided into symmetric or asymmetric. Symmetric means like the compression and decompression take the same amount of time. So if you're doing Skype, you're doing a Skype call, you probably want to have a symmetric compression, because the sender and the receiver take the same amount of time to decode and encode. Otherwise, you will have the like a choppy communication, like wait, and so on. But in some situation, you actually want the asymmetric compression. For example, you can compress a digital library, burn it to the CD-ROM, or like burn it into a repository for reading. Then the compression time can take a long time, as well as decompression and retrieval is fast. You don't really care. So in that case, you will want asymmetric. So like you are encoding your download movie DVD, encoding usually take a long time, but when you watch it, it's much faster, it's real time. That's asymmetric. Sure, you guys know it better than me. So other terms. Now, the code. So the final code, you encode it, you have the code word. A code is distinct if each code word can be distinguished from every other. So you find a 1-1 mapping. And it's uniquely decodable if every code word is identifiable when immersed in a sequence of code words. So give you an example. So say we use a bit 1 to represent A, 10 represent B, 11 for C, 101 for D. To encode A, B, C, D, just put all the bits together. So 1 for A, 10 for B, 11 for C, 101 for D. To decode, how to decode? Can you decode? Can you decode or not? No. Very good. No. Well, you can answer yes too. You can decode, but more than one. So, easily you can see that the first one can be A, 101 can be D, 1 can be A, 101 can be D. So there are multiple interpretations of that. So you can have the code word that can be distinguished from each other, which is 1-1 mapping. In this case, it is 1-1 mapping. But when they emerge together, it doesn't mean that they are decodable. Okay? So it's important that when you guys write a program to encode stuff using bit patterns, you need to make sure they are also decodable. It's not just 1-1 mapping, it will be decodable. It's not. The problem is when you're in a bit pattern, there's no divider, there's no delimiter between them. They're all together. So then you have the next concept, uniquely decodable. A uniquely decodable is a prefix-free code if no code word is a proper prefix of any other. So for example, 1 and 100,000 00 is uniquely decodable, but it's not prefix-free. Because 1 is a prefix of 100,000. So clearly, this is not prefix-free. Prefix-free means like you can't find any one of them is a prefix of any other. So this one, although it's decodable, it has some issue. It's decodable. If you have this bit pattern, can you tell what it is? How many COC in case you can't count? 8 zeros there. 8. Okay, the tips is like this is odd number of 0, this is even number of 0, there are 8 zeros here. So because of that, this one has to be 1 and good. Now, although it's unique, but do you want this? No, because although you can still uniquely decode them, it's so hard. When this becomes very long, and you are not just having 3 symbols, you have like, I don't know, 200 symbols, you're going to die. Because it involves you, try to decode that must be this way, and then you hit the bump. No, it's not. Then go back, try the other combination, and go again, and try it. Oh, that's it, this is the one. You don't want that. Although it's computable, but you don't want that, it's too slow. So you want something which is more prefix-free. Now, example. Is this one prefix-free? You tell me first. Great, good. So if I give you this, even it's very long, because it's prefix-free, what it means is like I can just look it up from here directly, because it's prefix-free. I can proudly tell you that the first one is B, without need to try all of them. And I know that's B, because it's prefix-free. You got it? Because it's prefix-free means like they won't have any overlap in the prefix. Then when you match it, it will guarantee that the one who matched that is the one. There won't be multiple of them match the same prefix. There's only one match it. So in practice, whatever mapping you decide on your code word, make sure it's prefix free. Otherwise, you have lots of pain. All right. There's a static code and dynamic code. This week is static code. Next week, we'll talk about dynamic code. What does it mean? Static code means like the mapping is fixed before the transmission. That's static code. Means like before I transmit, I say CO1 is B. Throughout the whole transmission, whenever I say CO1, it means B. That's static. Next week, we'll talk about dynamic. What does it mean? Dynamic means like now CO1 is B. Later, CO1 is not B, it's A. And later, CO1 will be Z. That's dynamic, it's changing. And there's an algorithm to do that. So sometimes the dynamic one, you can also use it as almost an encryption because the bit patterns for the alphabet is changing. And we can do it for compression too, but that's next week. All right. For the static code, such as Huffman coding, we're going to describe soon. It's static, it won't change, but you need to know the probabilities or distribution of the symbol beforehand. I need to know how many A there, how many B there. Dynamic code, as I said, will change, the mapping will change over time, and we also call it like adaptive coding. The idea is to exploit some locality of references and change the mapping dynamically. So we talk about dynamic Huffman, that will be next week. All right, before we start any serious method, one thing I like to tell you is how to measure. I guess before we are going to talk about arithmetics, it's good that I tell you that we can measure things by a ruler. How to measure? What does it mean by longer or shorter? You need some measurement. So the way to measure a good compression or bad compression is by what? By compression ratio. But you can't just use compression ratio. What I'm trying to say here is I give you a file. That's 1 gigabyte. I give you a text file 1 gigabyte. And now I can compress it to 200 megabytes, 5:1. How do you know that's good or bad? What norm you use to tell me that 5 times compression ratio on this file is good or bad? Now, you may do it like, give me a moment. Then you secretly try WinZip or gzip. And you find that gzip can do, similar. Then you say that, okay, quite good, as good as gzip. But that's not how we're going to evaluate, because if let's say you are going to have the world's best compressor, you want to submit a patent. Let's say you guys, after you listen to this lecture, you find that this is the cash cow. I'm going to write a patent tonight. But when you write a patent, you don't know how good it is. So if someone gives you a file and it can compress it, let's say 8 times of this file, how do you know that whether it's good or bad? So there's a measurement for that. There's a measurement to tell you that, like, given this file, anyone in this world can only compress it down to 491 meg. Anyone who tell you that less than 491 meg, they cheat you. It's a scam. There's a measure for that. Yes, that's entropy. Many people heard of that term, but to use it, that's what you use it, to measure how good is your compression. It's the entropy. So we use the runtime, your big O notation you learn from algorithm to do algorithm complexity. For the amount of compression, we use the redundancy or compression ratio. You can tell like 5:1, whatever this amount. But how to measure how good is your compression performance? We use something called the entropy. So the measure of information is from the person who invented the field of information theory, as I mentioned before, is from Shannon. So consider the symbols, one of the symbols called SI, and the probability of that occurrence of each symbol is PSI. as a probability of SI. In case of the fixed length coding, the smallest number of bits you need is the log n bits of that symbol. And n is the number of symbols. So it's a fixed length, it's log n. So for example, if you have 5 symbols, you need at least 3 bits for that. I mean, 2 bits, you only have 4 possibility. So if you have 5 symbols, you need at least 3 bits for fixed length. Okay? So for ASCII, if you have 256 symbols, you need 8 bits. If you have 127, you need 7 bits. That's for fixed length. If it's fixed length and the equal probability, if you have equal probability, you can't use less than that. Now, if your length is not fixed, and we can do something called the entropy coding, which is the number of bits used to code symbols in the alphabet is variable, such as Huffman coding and arithmetic coding. Now, this is a great theory of entropy from Shannon. And as I said before, you can guess where's Shannon from. Of course, there's only one university can produce this entropy theory. We call it MIT. Soon will be UNSW, maybe from COM 9319. I mean, never know. So, which is exactly to study the minimum number of bits per symbol you require for a particular distribution of characters. So, this is the equation, and the log PSI here, if you inverse it, is the number of bits required for the fixed length for that symbol times the probability of that symbol happen. Then you sum to all the symbols in your set or in your file. You will get this equation. Now, I'll give you an example, then you know how to use it. Suppose that in your file, you have only 2 symbols, A and B. Suppose in that file, the proportion of A is 40%, the proportion of B is 60%. So you have 40% A, 60% B. Now to compute the entropy for this set for the file with 40% A or 60% B, then you put into this equation, the probability is 0.4 times log, this minus here is basically just like 1 over 0.4 plus 0.6 times log 0.6. Then you will get 0.97 bits. So which means like normally it's a fixed length for and a fixed probability for 2 symbols. You need 1 bit. But because we know that they're not equal probability, you need less than 1 bit. So which means like theoretically, the minimum number of bits per symbol you use is 0.97 bits for this file. This is the average per symbol. If any compressor, you tell me that you got a compressor, you can do this file for like 0.90 bits, you cheat. If you tell me that you implement a compressor that take this one, you can do it on average, is 0.98. You're damn good. Yes?
This doesn't take into account like patterns of like repeating A's and repeating B's, for example, right?
No, this talk about the best case.
Oh.
The best case. As in like, you have, I don't care how your pattern it is, especially your ratio is 40% A, 60% B. If you tell me that you got something better than this, you're cheating. So at least you have a norm. You know what it is. You have a norm. This is the minimum. The difficult pattern will only make it harder. Means that your number will be larger, but it will not be smaller. This is the best case scenario. It's a minimum. Then when we develop the tools, you won't just test it on one file. You test on multiple files. Then for each of the file, you have the theoretical minimum. Then you know how close you are close to it. Then you will know how good is your tool. Now, they will not publish it. I mean, if I'm doing GZIP or whatever, you will not publish it. If I guess no one will do it, but if you will do it, you can go to, given this file, I'm going to calculate the entropy, then put it in the GZIP, and then see, is it the right ratio? You can do it. I can make it become the assignment 1, but that's just too easy. Sorry. So then, and give you some feeling of how good is an algorithm. I think the aircon stopped. Is relative to a theoretical minimum.
So is this equation quite always the probability of A is 0, and there's only one.
Probability,
There's only one. There's only one.
probability is 0?
Yeah.
Yeah, you don't put it in the equation, the probability is 0. If something never happened, why you put it there? You're saying that the file will not have A, but let's calculate A. That's just like, no, you wouldn't put it there. Yeah. The probability can be close to 0, but will not be 0. Yeah. Yes.
I mean, he mentioned the same thing earlier, but I mean, this is basically the minimum number of bits you could have if those characters can occur in any sort of combination, as long as the frequencies are whatever.
Correct. Correct.
Because like you could imagine, for instance, like in English, like letter Q, for instance, almost always occurs before the, followed by the letter U.
Yeah.
So, like if you looked at the separate probabilities of occurrences of the characters,
Yeah.
It wouldn't be taken into account the fact that they always tend to occur together. You know what I mean? I mean, if you calculate the probabilities just based on the
No. That will be different. So if you fix that, for example, if you assume that QU is always together, really always together, then in that case your QU itself is probably almost like one unit of it. Will be itself is like a symbol.
Yeah.
Now, if they are not necessarily together, then you can't assume that they are 100% together. That's a different story. You will still not get to the minimum. The minimum is assuming as far as you partition that AB is a symbol. This AB itself, it could be one letter, it could be 4 letters, but as far as it's one unit.
Right.
The unit A, the unit B, the probability that the unit A appear is 0.4, probability that the unit B appear is 0.6. This is the minimum. You can't use less than that to capture all the cases.
Yes, I'm just, it's interesting. I'm thinking maybe things like conditional probability, like, Q and U is an extreme example, but
Yeah.
if you know what a certain character is in the text, then
No.
that would perhaps allow you to calculate the probability of the following character,
Yeah.
which would be different to the probability of that character, in the text as a whole. If you know what I mean?
Once you say, for example, if all of them, let's say give an example, if I give you a file that's there AB, 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 they're just AB, AB, then one will just represent as just AB as one thing.
Yeah.
Then in that case, you're not having two symbols, you're having one. It's called AB. In that case, because, so, you are not just testing one file, that's called AB, AB, AB. If there's only one file, there's no information, that's it. You can assume the whole thing is one symbol.
Yeah.
So you need to generalize it to test it all the file with the distribution that is 0.4 and 0.6, all the possibility that will require minimum 0.97.
Yeah, so I see what. Yeah, just wondering. Like if you take TH, for instance, like in English, would that mean you might consider that as being one character? If it's like you might have like a separate character for TH, like you'd have TH and then TH as a separate.
No, so if you design it, for example, if you design it, you can play around with the mapping. Say, if you find that there are lots of TH, you can consider TH as one symbol, and there may be occasionally some TR. You can consider TH is one symbol, TR is another symbol. Every symbol can be more than one character. So then it's just, you map it to the different representation and see the number of combination of them. Then it may be the set is smaller, maybe larger, we don't know. So if I don't consider a pair of character, maybe I have, I don't know, like how many symbols, 1, 2, 7. But if I consider the pair of them, maybe the variation of them is only like 86, then you're better off to consider a pair. But if not, then I'll consider them individually. You got to gain something. By considering multiple of them, your set of alphabet should be smaller, not larger though. Yes?
So you're saying like you could consider them as pairs or not as pairs?
Correct. Correct.
I'll give you two different alphabets.
Yeah.
And then you put those two different alphabets through your
Yeah.
equation, then
Yeah.
wouldn't you get two theoretical minimums?
Of course, it would. If you have the different setting, because your set is different, the alphabet set is different, you will get a different number. Yes, it will be. The distribution will be different too, because you consider the pair and individually, the distribution will be different. It's almost like the same exercise. But that's a valid question. So I can give you an exercise. For example, the file have A, B, A, B, A, B, A, B, and something like that. I ask you to calculate. The first, calculate the entropy assuming A and B are individual symbol. Second one is assuming AB is one symbol, ABA is the second symbol. You calculate entropy. That will give you the different distribution and different answer. So it depends on which one is better off. But remember, this one here is not saying that like a particular symbol will take 97. This is assuming you test on all the files. As far as the file conform to this distribution, the average number of bits it takes is 0.97. It's an average. The minimum, average minimum. Now, we can always come back and discuss more when you see more examples. When you have the maximum uncertainty, when you have the maximum uncertainty, it's like if you say you flip a coin 50-50, that's maximum uncertainty. As in, if they're not biased to either side, or not, if all the distribution, all the probability are the same, that's the worst case. Then you don't know, you can't take advantage of that. That will give you the maximum uncertainty, and that will give you the largest H. This is the worst case. We design ASCII from the Shannon theory point of view. We assume every character have the same chance appear. So you assume that you will see the space bar as often as you see the character Z. So we assume the same probability. You put that into the Shannon equation. The P will be 1 over 256 ASCII. And the probability of that will be 1 over 256, but the sigma is totally 256 of them, will give you exactly 8-bit. So when you use the Shannon entropy theory correctly, even on an equal probability case, you will get at least, well, we will get the case when it's a fixed length and a fixed probability. That will tell you that for ASCII code, 256 symbols, you need 8 bits. But that's already the worst case. It means like if you want to take advantage of the ASCII distribution, we see more A than Z, or we see more alphabet than those funny symbols, you can change that. You can make it use less than 8 bits. But unfortunately, in our industry, we don't want to use it less than 8 bits because variable number of bits is harder to process. But it means that for efficiency, if you really want to store your information for space constraints or for transmission speed or for whatever, you will never store the alphabet as ASCII. It will be always variable length. It will be smaller. This is the worst case already, remember. The entropy gives you the worst when they're equal because it's uncertain, the most uncertain situation. Are you with me? You either with me or you are having a good sleep right now. All right. Another person you should know. Unfortunately, this person is also not from UNSW. It's also from MIT. It's around the same time. That's Dave Huffman. It's best known for the invention of Huffman code. It's a highly important compression scheme for lossless variable length encoding. It was the result of a term paper he wrote while a graduate student at MIT. Means like he's like one of you guys. Well, if you're in undergraduate, he's not like one of you guys. If you're in postgraduate, he's like one of you guys. So means like one of your assignment could be the future Huffman coding. So the idea I always like tell the students is like, you know, the only thing you miss in your life is like you were born too late. If you were born like, I don't know, 50 years, I guess 60 years earlier, you could be just David Huffman because the algorithm wasn't that sophisticated. It's just like you were born too late, everything becomes so hard because all the easy thing has been done. And that's just life. Okay? Well, you know, you can't complain. You would do the same thing. I mean, if there's a hard thing and easy thing, which one you would do first? Of course, the easy thing first. So all the easy thing taken, there's only hard thing left. So you look at like, if you study this kind of classic algorithm, they wouldn't be too hard because as I said, they would do the easy thing first. So it's not too hard. So the Huffman coding algorithm, when you have lots of symbols in a file, they have a different probability. You pick the two least probable symbols, the two rare symbols first. And because you want to take care of them first, it will generate the longest code word with the equal length and different in the last digit. And then combine them together to form the same symbol and repeat. That's it. Just 2 steps. So I show you an example, then we know how Huffman coding works. Suppose that you have 5 symbols, A, B, C, D, E. Suppose that their frequency is like you have 30A, 30B, 20C, 10D, 10E. What the algorithm tell you? Pick the least probable 2. Which are they? D and E. These are the 2 victims. So you just throw all the symbols here, pick the least probable first, D and E, add them together, or merge them together. Means like the chance to have D or E is 20. Totally 20 of them. So after you've done that, you count again. Pick the next 2 least probable out of that. You assume this combined one is as 1, not 2, as 1. So which are the least 2 probable? Is C and this combined one, because they are 20, 20. Okay? Then you combine them. Oh, sorry. Then become 40. Then assume this whole branch of tree as 1. Now you have 40, 30, 30. Which are the 2 least probable ones? Oh, sorry. So then this one. Then which are the 2 out of the 2 left? It's a funny question. 100. So after you form this, we call this a Huffman tree. And the rest of it is very easy. Left-hand side 0, right-hand side 1, that's it. Label all of them. Then from the top read to the leaf node, there's your encoding for the symbol. So for A, it's 0, 0. For B, it's 0, 1. For C, it's 1, 0. For E, it's 1, 1, 1. Then you get the Huffman code. Now, what Huffman code guarantee that with this simple algorithm is like the least probable one will get the longer length because it will be further away from the root node because you done them first. So it's a natural, easy, intuitive algorithm, and yet it gives you the intuition that if you are more popular, you'll be closer to the top because you'll be the last one we process. Okay? So, funny with these things, if I calculate the length, the average length of what we have used here, 2 bit for 30, 2 bit for 30, 2 bit for 20, 3 bit for 10, 3 bit for 10, you add up together, average length, you're using 2.2 bit for each symbol. So it's better than using the fixed length one because we have 5 symbols. Remember, we need 3 bits. If you're doing the N2P, 2.17. What's that? 2.2. Theoretical minimum, 2.17. Not bad. So if you're using Huffman there, as I said, it's a very simple algorithm. It's actually quite close to theoretical minimum. And it's not hard to write that program either. And that's why, you know where's Huffman algorithm right now? In some of the technology you don't use today. Fax machine, modem you're still using. In your mobile phone, every mobile phone has a modem inside. You probably don't know, but there's inside. It's a chipset. It's there. High definition TV, in case you don't watch, you watch the low definition one, then probably no. If you're using high definition one, yes. So there's a bit of Huffman everywhere. Another example. Suppose you have 4 symbols, A, B, C, D. They have a frequency 4, 2, 1, 1. You put it into the entropy. It gives you 1.75. You try to encode it using Huffman. I pre-compute it. This is what will be. So it will be 1.75. So the average length in this case for Huffman is identical to entropy. Yes?
Don't you also need to consider like storage of the tree, like the mapping?
No, we don't store the tree. End up, we will only store this, but you do need to store, you're right, we need to store the frequency, but not the tree. So that's why previously we said that for the static code, you need to pre-compute the frequency. And you need the frequency table. And that's the similar stuff that when you do gzip, there's a table overhead, like a header, which is the frequency. But you don't store the tree, because using that, the receiver side will compute using the same step, you get back the same tree, and you know how to decode it. Yes?
Why wouldn't you just store the mapping table instead of the real distribution? Wouldn't that save a lot of space?
You can. You can store the mapping table too. But later, I guess you will, we can, I mean, whatever you store, that's your software design decision. I really don't care, because that's your decision how you implement it. But what I care is like, because when you patent it, you don't patent how you implement that. You patent the idea of that step. It's how you, that's the step is how you patent it. Yeah. Those how you implement your assignment, really I don't care. Yeah. So now there's still some issue, so we try to change it. Like, let's say if they are all close to the worst case, means like similar chance. What will happen? Similar chance means like close to equal probability. So just to make it easier to calculate for me, a lazy person, so they all add up to 100. So when they are very close to each other, I still pick like 19 is the least probable. After you add, become 38. Then when it's 38, 21, 20, 21, so then I just pick a random 20 and 21. Then you have 41, 21, and 38. So 30 and 21 is smaller. So they add up, then become this two, you have this. It's the same steps, then you have this tree. Now with this, you still have a, sort of like, you have a longer bit for the least probable one, but they are cutting very close because the frequency that DE appear is very close to the frequency of AB appear. So by using longer bit and shorter bit, the difference is not that much because there's equal frequency, very similar frequency. So in this case, you will find that like the, if I'm using the Huffman, the length will be 2.38. If I'm using the entropy, it's 2.32. It's not identical, but it's still quite good. Not identical, quite good. Now, when is it bad? This is bad. Why is this bad? Let's try to run the algorithm. You can do this algorithm easily. I tell you, in exam, if you have a Huffman algorithm, sorry, if you have a question on a Huffman algorithm, you don't know how to do it, I will give you a 0 for the whole exam. Because this is just too easy, and you still lose the marks. I'm not saying you make careless mistake, that's fine, but I'm saying that you don't know how to do it, empty. That's just wrong. So pick the pick the least probable one. 1 and 1 add together is 2, and then you do the 2, and then you do the 6, and then you put this in. So you have that. And it looks fine to you, because the popular one, you use 1 bit, you can use less than 1 bit. So then the other like less popular one, you use more bit, it looks fine to you. But then when you put it in in fact, it's already quite good. Using Huffman is approximately 1 bit unit per symbol. Unfortunately, when you put it to N2P, it's close to 0. What does it mean? It means that theoretically, if the file is just full of A, there's not much information there, we shouldn't use that many bits to represent. And yet, we still need to use 1 bit per symbol. And then you know how many symbols there? There's 100,000. So that means the whole file, it still have lots of bits. So something wrong here. You know what's wrong? Because something wrong is that Huffman still requires at least 1 bit. That's where the problem is. So we need to find a method that uses less than 1 bit for a symbol. Can we? Running. Can. That's one of them. Good. Anything else? That's good. So, but we have something even better than running. Huh? What? Not using?
Not use symbol for A. And you need, for example, where is B and where is C?
Use the value B and C?
Where is B and where is C?
We just need to recall the position of B, C, D, and...
I see. Yeah, good. Great idea. I didn't think of that. That's good. You should patent it. Yeah, it's good. Yeah. So, but when you patent, remember, like patent useful stuff, because any file with that is a loser file. Like, it's not very meaningful. With the file, basically, this kind of file, there's not much information there, should just delete them. But it's a good idea. Good idea. So, right. So the problem with this Huffman, of course, not better than all you guys' suggestion, is because it requires an integral number of bits. So in the minimum, you require 1 bit, or 2 bit, or 3 bits. So it requires, it's an integral number of bits to represent the information. So even sometimes, theoretically, you may only require 1.5 bit on average, but you can't do it with Huffman, because Huffman will need to 2 bits. It's an integral number of bits, so you can't use half of a bit to store stuff. So in that case, it's not optimal. And that's why we require something which does not require integral number of bits as a unit. Hence, we got this arithmetic coding. Now, arithmetic coding, it was invented a long time ago, and it's known to be quite efficient. For example, inside JPEG, you know, everyone uses JPEG. Inside JPEG, they're actually using, one of the steps is Huffman. And because of they're using Huffman, because JPEG is for images, there are lots of extreme distribution of the symbols, very extreme. So using Huffman is not the most efficient. Using this scheme I'm going to talk to you will make your JPEG at least 1/4 more smaller of your images. But JPEG didn't use it. Do you know why? Yes. Good answer. In fact, whenever I say that this scheme is good, why we don't use it? You answer patent. 99% will be correct. So arithmetic coding, at least there are 50 plus patents on arithmetic coding is owned by IBM. There are much more patents on it by the other company. There are more than hundreds of patents on arithmetic coding. It's a landmine. So because of that, most of the technology, they avoid it. But one of the good things about arithmetic coding, later I will show you, those inventions are more than 25 years ago. They start expiring. So that's why in the past 5 years to 10, in the past 5 years or 8 years, you have more and more startup companies from Israel, from California, from US, they make better JPEG compression, decompression, lots of companies like that. It's not like, how come all of a sudden people just become smarter? No, it's not. It's just like they are not in jail anymore. So you are free to use those mechanisms without paying the license for the arithmetic coding. So this is one thing. So it's good that now we can freely discuss arithmetic coding. So if you want to use it, you can use it. So the idea of that is like, let's say we have the string called Bill Gates. And Bill Gates is, there's one space between Bill and Gates. And there's one A, one B, one E, one G, one I. Everything is 1 except L is 2. So it's a nice string, quite unique. So these are the probability. And they all add up is 10, easier to calculate. So except L is 2 over 10, the rest is 1 over 10. I'll show you the algorithm later. So the first thing we do is like, we have a number line between 0 and 1. We chop the range according to the probability distribution of those symbols. So because there are 10 symbols, 10 unique symbols, you chop it into 10 different sections between 0 and 1. Each section is 0.1. The range is 0.1. But because of L itself is 2 symbols, in fact, it's 2L. So L will deserve to have a range of 0.2 because it's 2 symbols, 2L. So 1 symbol, you get 0.1, 2 symbol, you get 0.2, 3 symbol, you get 0.3, because totally there are 10 symbols. So you divide the number line in this way. Then you follow a very complicated algorithm involving minus, plus, and times. You may not be able to do it without a calculator. So when you go to the exam, remember to bring a calculator, because if we have minus, plus, and times. Now, you laugh now. You laugh really now. 4 years ago, I have a student in the exam. He said that I actually know how to do this question, but I forgot to bring my calculator, although you want me 3 times. Could you please assume that I know how to do it? He wrote me this algorithm on the exam without the actual calculation. I can't. So you need a calculator because you don't know that plus, minus, and times can be so difficult until you see this. All right. So you can go home and read this algorithm because it's so easy. I'm not going to read it to you. I'm going to explain how it works, and then when you read it, it will be much easier. So the idea is that if you only have 2 symbols, A and B, and assume that A and B, they both appear equally, equal chance, then what I'm going to do is like I decide 0.5 is A. From the 0.5 to 1 is B. So if I tell you that 0.3, what does it mean? It means A. If I tell you 0.7, what does it mean? It means B. So then, if we do it in that way, we just have 2 symbols, A and B, they're equal chance. How can we represent AB, AB, which is more than 1 symbol? It's 1 symbol, it's easy. Less than 0.5 is A. More than 0.5 is B. But you want to stack them up so that you can have a string, concatenate all the symbols. Then what you do is like, within 0.5, further divide So within the 0.5, you have 0 to 0.25 is A. 0.25 to 0.5 is B. Then from the 0.5 to 1, you also divide half again. From the 0.5 to 0.75 is A. From the 0.75 to 1 is B. So if I tell you that is 0.6, means BA. Because it goes to the above 0.5, within the above 0.5. When you go above 0.5, what does it mean? It's B. Within the above 0.5, it's 0.6, so it's lower than 0.75. So it's A, so it's BA. Yes?
In reality, the precision of the number is limited by the slope number representation.
Correct.
So there's like only finite number of symbols.
Very correct. None of your comment is wrong, but we can pack the bytes together. So as in, I'm showing you here for explanation for the lecture. I give you a decimal unit. In the actual implementation, they will use binary representation. So when you run out of the space right here, let's say you use up 4 bytes, you use the next 4 bytes, continue using a binary representation. That's how they do it. In fact, it's a very good question because one of the patents is just talk about binary representation of AC. And that's also from IBM, by the way. So if I remember correctly, that patent is actually is called binary representation of arithmetic coding. It's not arithmetic coding. It's just a binary representation of it. So basically, if you know what it is, you go to read this algorithm. It just calculates exactly what we do. So for example, suppose that you consider the second L, which is after you have the first L, we are in a 0.256 and a 0.258 range. Then you got one more L. You want to calculate the value. So what it does is like the range between this is the range between the first L, which is this one and that one, the range. Remember how we chop the number line? We want to further divide it. So we want to further divide between 256 and 258. We want to further divide it. So you further divide it, you try to find where's the L position within that range. That's exactly what we are doing right here. So you further divide it, there's a 002, there's a gap, and that gap, the gap you times the 0.8 is the high range of the L. 0.6 is the low range of the L. You times the range, you get exactly where's the section within that range. This is how we compute all this. So when you do the algorithm, as I said, you read the algorithm. If we don't understand, then next lecture we can focus more on it. But it's exactly the steps of what I described to you. It's an inverse, this one. It's an inverse, means like I give you this number. You need to go through the steps. Where's that thing within that range for? So for example, this is 0.257. is between 2 and 3. Means this is B. The first letter is B. It's B. It's the same example as I told you before. Remember that there's just AB. You have up to 0.5, and then from 0.5 to 1. If I tell you there's 0.6, you know that the first letter is B. And then go inside to see where is it within. So it's exactly the same step. So, and there's an example for that, how to calculate that. Now, then you will tell me, I can have a very extreme distribution like this. Many A, one N of symbol or whatever symbol, or one symbol, odd symbol. So, but mostly A. So you have order A and then an N of string. We can encode this using this number. So that means any number between 0.43 and 0.47 will do. For example, I can call 0.45. That will, the value represent all this A in a file. Remember the same example as I told you before, like when we have the symbol AB and I use the 0.5, and then within the 0.5 to 1, I divide into up to 0.75. Whether I tell you it's 0.6 or 0.6666 or 0.62, you still get the same result, is BA. So here, you probably will choose the shortest form to represent that within that range. It's fine. Now, with the distribution, as I told you before, sometimes there's a fine line between compression and encryption. So I can encode your student name using arithmetic coding and send you an email. Hi, 0.65, how are you today? So it's really it's a fine line, depends on how you consider this. But as far as the final form we have is smaller representation than the source, we are considering doing compression here, because you want to use fewer number of bits to represent the original information without losing their content. That's one of the compression. This is arithmetic coding. It's one class of algorithm in compression. It's very famous. Now, from now onwards, you are the expert already. You already know two, Huffman and AC. And you can find that, like, if you look at the JPEG implementation, all the JPEG, inside there will be one part, one module. It's either called Huffman or called AC. Commercial one these days, as I said, because patent expiring, there are lots of them using AC. The old one, you will still see Huffman inside. So that's one component. Now, after, I'm going to stop soon, but after next week, you will have all the modules you need, like we'll cover a few more, LZW and so on. So you know all the different class of compression algorithm, you know all the advantages. As I said, they're not very difficult steps, but they work effectively. After you know all of them, you can play around with them. All the commercial compressor, they're just using maybe after Huffman, they're doing running encoding, then they're doing AC. It's just a combination of these steps. Then they will have a commercial compressor. Questions, guys? Yes?
I noticed with the arithmetic coding that you do need an end of file symbol.
Correct.
Otherwise you won't know when to stop.
Yep.
How would you calculate what percentage distribution you assign to that?
The end of file symbol?
Yeah.
So,
I presume it would depend on how, like the average length of each string.
it depends. Again, like the end of file symbol, you will encounter that in not just arithmetic coding. For all the compression algorithm we talk, you always treat the end of symbols in a special manner. So some implementation, they will simply store the total number of symbols in a file so that you don't need to worry about that. Some of them, they will really treat the end of file symbol differently in a sense that, like, they will, they either put the position where it is, or in arithmetic coding, usually in the statistics table, sometimes you don't store the probability. Sometimes you actually store the actual number of A, actual number of B, actual number of B. So there's a different way to calculate that. But because the end of file is more like to do with when it start, when it stop kind of thing, we always consider that's an implementation issue. It's not part of the algorithm though. So they don't really mention how you should deal with that. Yeah. So you're free to do anything again for that. Other questions? So guys, you have some idea already. Now this, if I ask you to implement the arithmetic coding, suppose that the encoder and decoder, and suppose that when you Google for the free source code you can't find, that will be the difficulty of your assignment 1. If you time set difficulty 3 to 5 times, that's your assignment 2. I don't know how you time set, but that's what it is. So I would say that like they are not hard in a sense that like, you know, I'm not asking you write the low level, you know, hard disk driver kind of thing, not like operating system, but and they don't involve very complicated steps that involve like, we don't even have square root. We only have plus, minus, times at most. Sometimes division maybe, but not even square root. And we don't have lots of hard, deep theory either. They're mostly steps. But we focus on the steps and why those steps, the understanding of why those steps. As I said, like, I don't want you to just memorize these steps. I want you to know why this step, as I explained to you, how it works. So in the exam or in anywhere, or you don't even need to memorize it, you can work out the concept. If you know the concept, how it works, it's not hard.
So implementing that, I guess that would include figuring out how to do the binary floating point as well.
Correct. If you're doing like that, then we'll be like those who don't do the binary representation, they were able to fulfill the assignment. But those who aim for the best of the best, they will have to go for the binary representation. That is a good question. So as in the assignment probably will not require you to do it in a binary form and give you the freedom that whether you do it in the decimal form, binary form, hexa form, whatever form you want. But if you come to ask me offline or something, or in the question and answer section, I will tell you that the best performer will be the binary form. That if you aim for example, bonus.
So the first assignment's actually going to do this algorithm or something similar?
I'm not saying that the first assignment is this one, by the way, though. Like, I'm just saying that similar difficulty. But this difficulty is assumed that you can't get the source code from arithmetic coding. But I wouldn't ask you because there are plenty of source code of arithmetic coding there. Yeah. So it won't be that assignment. I'm just giving an example. Yeah, it's that kind of difficulty. Assume that you cannot see the source code arithmetic coding, but you already understand it, you need to implement it, that it will be assignment 1. Yeah. Yes?
Sorry, just a bit of a general question.
Yeah.
You mentioned that data structures are essential, and I appreciate that. This is more, but if you're a bit rusty, is there any particular that's worth revising, which areas to look at?
The data structure, like, you don't have to look at it in advance, but the one thing I would say that you definitely need to know, say, what is a tree, what's an array, what's a hash table, what's hashing in general. I would say that like if you use them, you can, because this is not like a closed book exam, you need to use those data structure. It will be, you may use it in an assignment, or you may say that this part will be, we can implement as a binary tree, for example. Then if you don't, say you forgot a binary tree, for example, you forgot the performance something, you can still go back and go home and look it up. But it's just like relative to the other student, if they don't need to look up, you need to look up, you'll be slower. But if you actually hate those stuff, as I said, I don't recommend you to do this course.
I just more just a question of, is there any particular areas that we should actually refresh the data to be more focused on? For all data structures?
You definitely need to use array. I can't think of how you can pass this course without using array. You probably need to like good in like sorting an array or maybe finding something within an array. Some students can avoid pointers, finish the assignment before, so I don't think pointer is necessary, but I think array is necessary, and some file handling is necessary, like how to open a file, write to the file, open a file, those are necessary. And as I said, like if you're good in data structure and algorithm, like as I said, like maybe hashing, tree, sorting, searching. I'm not talking about searching this search, because if you know this search, you don't need to do this course. I'm saying just searching within an array kind of thing, and you should be fine. Yeah. Yeah. Yes.
Do we have to use C or C++?
Yes. It's a good question, but I give you a short answer. I like that. Like you have a very long question, I have a very short answer. That's compression. That's like many map to one. Yes or no? Yeah. But to standardize it, or otherwise, also we can't compare performance or runtime as a different language. It has to be the same. But you can use C or C++. You can use any packages that has been installed in CSE. Yes, yes. All right, see you next week.
Learn C++, so only C. So
It's fine.
So we don't do any oriented, just using
It's or C or C++. You don't need to use both. One.
C.
Yeah. Which one? Arithmetically? Yeah, yeah. Yeah. No, no. As the other girl asked, you either know that, for example, if there's some representation of the n symbol, or you know the total number of characters, as I said before, so you need to handle it. But that's not part of the algorithm. That's like you can do implementation whatever way you can do it. No. For example, like instead of storing a probability, you can store the actual number instead. Then you don't need to store the total because they add up with the total.
I mean, the final including number is taken from the results from the real.
Yes. Yes.
Number including text to know
Yes.
the
Yes.
ends.
Yes. You either know the total number or you know which one is the n symbol. So in this case, for example, because the n symbol is in the table, you know this is the n symbol. So when you see the n symbol, you stop. So you either have the n symbol or you have the total number. Yeah, yeah. Who's next? Yes. Yeah, yeah. It should be recorded. It's always. That's a very good question. It will be there when the first video is available. So it's how it works is like, usually when all the lectures is like that. So some lecture they will set up the Moodle first, some lecture they will wait until the first video available. When a video is available, the lecturer will receive an email saying that your video is available. They need to go to grab the video and put it in the Moodle and create. Then you'll get it.
How did you select this, in order of this list of characters you selected for the arithmetic coding? Because it was originally in this order.
Oh yeah, good question. That's a very good question. That's a trick. So you set the, where is it? That's a good question.
When did you?
That's good. So this one, I think it's just sorted alphabetically, but the order doesn't matter because if you're going to implement one, as well as the encoder and the decoder, because you wrote both of them, you follow exactly the same order, you can decode. So for example, you like to sort from A to Z, but I like to sort from Z to A. You and me cannot communicate. Means you encode, I can't decode. But your encoder, when you encode the information, you are the one who write the decoder. So you should follow the same order as you.
So I just choose whatever order I want.
Yes. Yes. But normally they will do alphabetically. In fact, it's not alphabetic. They will do the same order as the SE code in the SKey table. That commercially they will do it that way. But you are free to do anyway.
Also, when you do the work, reduce workload, then you must register the.
Any other questions, guys?
One more thing.
Okay, good.
One more thing.
Yeah.
So I think you need a question for the people.
Okay.
Next time, just ready for the people question. Otherwise, it's difficult for me.
Okay. All right. You just let me know what you have here.
Okay. Yep.
Get them to say it louder.
Yep.
So that's everything, but I will need to do. Yeah. Fine. Let me know. Okay. Let me know.
I mean, I really enjoy lecture.
Is it?
Yeah, there's a lot of jokes that you do. So I think myself.
Yeah, I already done this.
Maybe I'm not a waster. Anyway, let's see you.
But I haven't received. I haven't received any results SDI's result because they said SDI will send email to you.
So you already submitted it for?
Yeah, I submitted it. Not last Tuesday. Yeah, he told me you should they will spend 10 days, 10 work days. 10 days. Oh, you mean?
Pretty sure that we are both public.
No, I've already got that.
For me, I just got it for CSS.
Oh.
I think
You.
Oh, you submitted that form to the SDI
no,
2 weeks
no way
ago.
we can. I just went to see it.
Okay.
Do you work hard?
If you work hard.